Am I audible?
Yes, sir. Am I audible? Am I audible?
Yes, sir.
Yes, sir.
Okay. So today we will start to learn about the most critical, important part of microcontrollers, which you never experimented in other languages. If I ask any one of you, have you done interrupt programming? So general answer, most common answer is no. So we have not understood that method of programming, either in normal C, C++, Java, like that, generally. So when we use the controllers and start developing programs for embedded systems, it's a very common to use interrupts for data transfer. So that is why whenever we want to transfer the data from the controller, this controller, you may have so many devices outside the controller. You may have some sensors, you may have some intelligent devices like printer, you have some modem, so many other devices are there. So when you want to establish a communication between external devices and your microcontroller, what is a method available for all communication? This one. There are two popular methods are there. We call as a transfer of information between the controller and the devices. So one method is called as a program-driven data transfer. Other is called as interrupt-driven data transfer. Let's understand now what is a program-driven data transfer and what is an interrupt-driven data transfer. No. So program-driven data transfer is basically with the help of program, you try to check every device. Do have the data? Yes, if it's a data is there, read the data. That means that we call as it's called as polling method of data transfer. Polling. In the program, in the loop, you poll every device. Do you have the data? Then read the data. Because you do not know that whether the hundreds of devices, hundreds of sensors connected to the microcontrollers, do you have the data or not? You do not know unless you talk to them. So that is talking to these devices. Talking to the talking to these devices through the program and getting the data from the devices or transfer the data to the devices is called as a program driven data transfer. There is another method is available that is called as interrupt driven data transfer. Here microcontroller is sleeping, in the sense it is not doing any other job. It's just waiting for the request from any of the device for the data. As soon as it gets a request from any of the device saying that I require your service, what does the controller will do? Controller will execute a service routine meant for the device which is requested, get the data, and then finishes job and again wait. So microcontroller is always sitting idle or sleeping. So only when the request is come, then only it performs the data transfer operation. It is called as an interrupt-driven data transfer. What is an advantage of program-driven data transfer compared to the interrupt-driven data transfer? There is no specific advantage is there compared to the interrupt-driven data transfer. Because why? In the program-driven, control is continuously engaged, it's looping. Only thing is, they don't require interrupt mechanism. If even the interrupts are not there, program-driven data transfer works. What is the disadvantage of program-driven data transfer? So a lot of time of the microcontroller is wasted in polling. You should be always in the loop, and the latency will be less. Latency means time taken by the microcontroller to service the devices will be late. Because if there are 100 devices there, you start for one device, go to the second device, go to the third, go to the 100. You are polling every device in an order from 1 to 100. By the time you finish 100, then only I can go for the 1. So the more number of devices are there, the latency will not improve. In the sense, the time required to attend the service of the device, that is called, we use the word called latency, will be more. That is, more time is required. So then what will happen when very important sensors are there, when important things has to be attended immediately, you cannot attend that service immediately by the microcontroller. So you lose the data or the service is delayed. So that is a disadvantage of a polling method. So the other disadvantage is programmer has to write the code, adding it. There's a lot of manipulation on the programmer side is required to adjust the timing for every device. And it is difficult to always do other jobs. When more number of jobs comes, you have to interleave the jobs properly. So it's a challenge for the programmer. The latency can not be ideal or cannot be improved at your will. These are some of the disadvantages of program-driven data transfer. Let's assume that there is a concept called interrupts is available and interrupt-driven data transfer is available. So let us understand first what is a interrupt and understand what is interrupt-driven data transfer. That means that, say, this is your ARM CPU core, that is ARM 7 CPU core. So this CPU core establishes a connection between so many devices. See that there are about more than 10 to 15 devices are there, and each device internally contains so many other submodules are there. So many devices are there. All these devices has to talk to your microcontroller or the CPU core. Now, in case of an interrupt-driven data transfer, what will happen? This microcontroller is always executing one program, always written by the programmer. So that program we call as a main program. We use a word called as a main program, or I will call as a MP, main program. So let's say always you're executing this program. So the program counter sets to the beginning of this one, it starts executing this program. Now, whenever there is a request comes from any of these devices which is surrounding the core, number of devices are there. You may have a request from ADC whenever the new data comes into picture. You have a timer is started, timer can overflow and timer informs that now it's a time for attending the timer. You have a PWM. So many UART is there which talks to the computer. Whenever you get a data from a computer, you should inform to the ARM core. So lots of devices are there around the microcontroller. When any of these devices has some data available, has some action to be performed on the microcontroller, it immediately, what does it do? It requests the microcontroller. So to request the microcontroller to provide what is called as a facility to get this request. So that facility is given in terms of hardware pins or the hardware facility, which is provided for any CPU core. We have studied in the ARM 70DMI core, there are two interrupts levels are there. There are two interrupts are there. What are those interrupts? One is FIQ, the fast interrupt request. So other is called as IRQ. So these are the two interrupt requests which are available for the core of ARM CPU. So ARM 7 is available. So what is this? These are the two requests which can be accepted by this ARM core. Then what will happen? The requests which are coming through these devices will be directed to one of these pins. That means that as soon as it comes, it will give it to what? So either to the IRQ and FIQ, then immediately as soon as it receives the data or the request from these pins, the microcontroller stops this program wherever it's doing. It stops here. It stops here immediately. Then what it will do? It attends the request generated by the device through FIQ and IRQ. What is the meaning of attending the service or attending the device? Again, there is a program should be there. We call now onward that program as a service routine. Since the service routine is returned for the interrupt request, we call that program as now onwards ISR routine. So what is an ISR routine? ISR routine is another program. It is a program returned to service the devices which has raised the request. Now, as soon as it stops, what will do? What will happen? The microcontroller stops it and immediately branches to the ISR wherever it is there. Correct now. So this branch, it finishes the complete interrupt service routine, and then again it comes back to what? The place wherever it is branched there, and it continues here. So this concept is called as interrupt. If somebody asks what is an interrupt, I can define like that. Interrupt is a request to the microcontroller CPU core to stop the execution of the main program which is executing and attend the device by executing the concerned interrupt service routine, and then finishes the ISR, return back to the main program. This is called as a definition of an interrupt. So interrupt is a request to the microcontroller CPU core to stop the program execution, whatever it is doing, attend the service of the device which has requested the interrupt by executing a suitable interrupt service routine, and then branch back to the main program. So this is called the definition of an interrupt. Now, so whenever I know that this is the definition of an interrupt, then what comes to the mind is, now, if this is an interrupt service routine, it's available, and which is you are executing it. Now, what is the difference between calling a procedure and interrupt? Say we call many procedures in the main program. How do we call the procedure from the main program? So you can look at here. This is the some program I written for generating a 1 kilohertz waveform. Sorry, if there's some 50 hertz waveform I have written this program, let's say. Now, how does this work? So this works like this. So whenever I do some job, I set the pin 1, and then I'll call the delay, set the pin to 0, and then call the delay. So if you look at this type of programs, you are explicitly invoking a procedure name, then you're branching to that place, finishes the execution, and come back to this place. This is called procedure. Then what is the difference between a procedure and interrupt? This is a common question you should be able to answer. A procedure is explicitly invoked by the programmer whenever he wants a particular service, whenever he wants a particular logic to be executed. Whereas here also, main program, you're stopping it, you're branching to ISR and executing, come back. But what is the difference between a procedure and ISR? In case of a procedure, you are invoking explicitly by calling an instruction, by calling the name of the procedure. That is, you know when you're calling it. Whereas in case of an interrupt, when ISR is executed, it is you're not explicitly calling here. I'm not calling like delay, I'm not call. So that means that when you're executing a main program without your knowledge, so immediately it branches to the ISR and come back. That means that I am not explicitly invoking the procedure. I am not explicitly invoking the procedure called ISR. Then when does it be called? I do not know. So the programmer who writes the main program do not know when this ISR is executed because you have not written a code in the program called the name of the ISR. So that means that I have not written a program called ISR. I have not written any routine called ISR like that. I have not written name of the ISR here. Let's say I have a program called ISR is there. I'm not calling the ISR here. That means that even though ISR routine is there, I'm not calling in the program. Then when does it execute? Whenever the interrupt is generated through hardware. It's very important. Through the hardware logics present, interrupt logic present in the core, then immediately microcontroller understand that it is a request now coming from a devices. I should stop. Randomly, wherever it's executing, stops the program at that point of time and then immediately branches to the ISR. So this is the difference between procedure call and interrupt series call. Procedure call, you are invoking explicitly. Interrupt series call, you are not invoking in the program. It is through a hardware mechanism. Through that, it just stops the program at any point of time. You do not know where it stops. So whenever it comes, it stops, executes, and come back. So ISR and procedure, what are the common features? For both procedure also, you should require a code. For ISR also, you require a code. In case of procedure, you explicitly invoking. In ISR, it is invoked at the hardware level. So this is the meaning of what is the difference between a procedure and a interrupts. Now, let's understand in detail about the interrupts. Now, so whenever you have devices which raise the interrupts, the question is, it is not the 1 or 2 devices are there around here. If you look at here, you can look at here. There are so many devices are there. There are so many devices are available here. So look at the devices, whatever you have. How many devices you have? So many devices you have. So many devices if you have, then how many pins of interrupt pins available for the core of ARM? You have only 2 pins are there. One is FIQ, other is a IRQ is available. That means that I have only 2 pins available here, IRQ and FIQ. But so many devices are requesting for that. When there are so many devices are there, which one, if the more than 3 devices request, which one I have to select? And how do you select one among the many? And how do you pass that information to the core using only 2 pins called FIQ and IRQ? So for that, there is a hardware logic is required. Through that logic, I can able to use multiple interrupt requests, select one among them and direct to the FIQ and IRQ. So that logic is called as vectored interrupt controller. So this is the logic. So what is a vectored interrupt controller? Vectored interrupt controller is a hardware logic or a hardware mechanism or a hardware module which has got so many registers inside that. So it receives the request from all these devices, many number of devices it receives the request and select the required one among this one, and then it generates an interrupt request to the microcontroller through the pins called FIQ and RFQ. So what is vectored interrupt controller? It's a hardware mechanism which receives the interrupt request from many sources in the microcontroller chip, including, when I say many sources, not only internal sources, external also. So this LPC2148 has certain pins called as 4 interrupt pins available. That means that devices which are outside can generate a request through these pins. How many pins are there? External interrupt 0, 1, 2, 3. So 4 external interrupts pins are available. If you have a request from the devices which are outside the microcontroller, from the printer or from the computer or from the other sensors, so any devices, so you can connect them to these pins. We are called as the external devices, and these external devices, as soon as it raises the request here, let's say 0 to 1, you make the pin 0 to 1, immediately what will happen? So this identifies there is a request is coming from a device. So immediately it raises the request through the vector interrupt controller and sends that request to the ARM core. Then ARM core identifies that one, stops the program and attends the service required for this device. The service can be reading the data. You have some important data, that is why you raise the request, interrupt request. So then what will happen? Read the data and then continue execution whatever you want it. So vector interrupt controller receives the interrupt request not only from internal these peripherals, also from external devices through a pins called external interrupt 0, 1, 2, 3. Then it selects among these many and generates FIQ and IRQ interrupts. Let's go into little more details now. Now, whenever the concept of interrupt comes into picture, there are 2 classifications of interrupts we do it. One is called as maskable, non-maskable interrupts. The first concept. What is a maskable and non-maskable interrupts? Let's say I have a request from over 32 devices. Actually, there are 32 different sources of interrupts are available inside the LPC2148, including the external interrupts, 4. So including these 4 total sources, that means the total different places from where the interrupt can rise is 32 as well. That means that if somebody asks how many requests can interrupt controller can read at a time, it's a 32 interrupt requests coming from the different devices. 4 from here and the different other things available, timer 0, timer 1. So PWM, A to D converter, like that. Every block generates an interrupt whenever some activity happens. So totally there are 32 interrupt sources are available here. Now these 32 interrupt sources, whatever you get from here, sometimes I may not be interested in some interrupts. For example, I am doing an important logic. For me, the external interrupts are not important for me. So I should be able to have a provision to disable these interrupts. I'm not interested in the timer 0 interrupt. I should be able to disable that logic. I'm not interested in the computer connection now, UART. So I should be able to disable that one. So selectively enabling or disabling the 32 interrupt sources which are coming to the vector interrupt controller, this facility is called as maskability of interrupt, masking and unmasking. So all the interrupts, whatever the 32 interrupt sources you have in the LPC2148 are called as maskable interrupts. So there are some microcontrollers where the interrupts cannot be maskable. In 8086, the Intel processor, there was an interrupt. So NMI, non-maskable interrupt, you cannot stop it. When it comes, microcontroller has to stop the main program and branches to the ISR of NMI. No way could have stopped it. So that is one such interrupts are also available in the microcontroller. So it's called as non-maskable interrupts. So in case of LPC2148, all the interrupts, whatever you have, are called as maskable interrupts. That means that through the program, I can enable or disable interrupts. How do you do that one? There is a register is provided inside this microcontroller. It's called as interrupt enable register. In that register, whichever the interrupt I require, I have to make it 1. Only when I write 1 in the corresponding bit, because I said 32 interrupt sources are there. The register is a 32-bit interrupt register, enable register is there. Every bit in the interrupt enable register controls enabling or disabling. By default, all the interrupts are disabled. Whenever the programmer requires, you can write 1 into the corresponding bit to enable the request. So that is called as maskable and unmaskable interrupts. If somebody asks whether the interrupts are maskable in LPC2148, yes. In ARM 7 CPU core, all the interrupts are maskable in nature. By writing it to the proper register, I can enable or disable it. Let's go to the second concept. What is it? Vectored and unvectored interrupts or non-vectored interrupts. What is the meaning of a vectored interrupt? So, for example, an interrupt request is raised here. An interrupt request is raised by the device. Now, you would have written an ISR for that. How many ISRs I would have written? So I would have written ISR 1, I would have written ISR 2, I would have written ISR 3, ISR 4. So effectively, how many ISRs you can have? If there are 32 devices are there, 32 different programs can exist because the service you are going to do for every device which raise the interrupt may be different. Maybe the service what you're providing to the printer is different. The service what you provide to the computer when it requests is different. The service what you provide to a timer is different. So that means that all 32 the programs or interrupt service routine for different devices are different. So when you have many such routines are there, whenever you raise an interrupt, as you select among the 32, I said you have to raise either into FIQ or IRQ. Let's say you have an FIQ interrupt is available. Let's say you have an FIQ interrupt is available. Now you are receiving the many number of interrupts in the vectored interrupt controller, and many devices have requested it. Now, as soon as you raise an FIQ, how does the ARM core knows that which device you have to service it? Because if there's no only 2 pins are available, but the devices are many. So when you get a request, how does the microcontroller knows which is the device it's requesting? Number one, and as soon as it knows which is the device, how does it know that which ISR program it has to jump? Because you are in the main program, you are executing the main program now. So from the main program, you have to branch to where? One of these ISR. But how does the microcontroller knows which ISR it has to execute? So that is always the challenge. So for that, if the address of your ISR can be defined by the programmer, then it is called as what? Vectored interrupts. So what is a vectored interrupt? That means that the programmer can define which is a routine it has to branch, that is where it has to branch in the memory. So for the interrupt, then that interrupt is called vectored interrupts. If there is no facility for the programmer to locate their program wherever they require it, there is a fixed memory location. Let's say fixed memory. So memory is, what is the memory? Total memory, 2 to the power of 32 minus 1. That is the size of the memory, 4 GB memory. If the microcontroller specifies that whenever you get an interrupt request from this pin, please go to the memory location called 1000 and you execute it. If they would have fixed it in the microcontroller itself, for this interrupt, this is a memory location where the program has to write. That is called as, so where it's a fixed. That means that you have to go there, you have to specify that there is an address is associated with the interrupt request. So in case of non-vectored, that means that address is not specified, address is not known to the microcontroller. The device which raised the interrupt should be able to provide the location where is my routine is also available. So that means that vectored and non-vectors correspond to what? Whether there is a mapping between the ISR and the interrupt. So if that mapping is provided, we call it a vectored interrupts. So let's understand more about these vectored interrupts, the Maskable interrupts more by just understanding how do we write a interrupt service routine program now. Now let's start understanding the programming of the interrupts, interrupt driven data transfer. How do we do it now? So before I start the program, some of the concepts about the interrupts. How do we classify these interrupts? What are the levels are there? How do we enable them? How do we disable them? How do you map an ISR address to a particular interrupt? That we will learn little basics and then we'll go to that one. So let's go to this is the manual. What I'm referring is an LPC2148 user manual. It's available in the net also. You can download this. So any module or any portion of the LPC2148, you want more details, you can always learn about you can download this manual, you can learn that. This is a reference for all our notes. So we call it's a vectored interrupt controller, VIC. So this module is called as vectored interrupt controller now. So let's learn some basics about that one. As I said, total number of interrupt requests which is coming to the vectored interrupt controller is called as 32 interrupt requests are available. And in this 32 interrupt request, it also facilities there called as vectored IRQ interrupts. That means that 16 can be vectored IRQ interrupts. 16 are vectored IRQ interrupts in the sense you can map so your address of a ISR to an interrupt. That means that whenever interrupt comes, in case of vectored, you are specifying that it has to go to this particular place. You would have mapped in the program. So that is called vectored IRQ interrupts. Now, there is when many number of interrupts comes into picture, we use a concept called priority. That means that if there are 16 interrupts, vectored IRQ interrupts are there, let's say that if the interrupt comes from all the 16 devices at a time, I can able to handle only one IRQ. That means which among the 16 I have to select it. So if you are able to provide through a program a facility to prioritize the interrupts, that means that, so I can say that I can define through a program. So this should be 1, this should be 2, this should be 3. So if that type of priorities are defined and facility is provided in the microcontroller, then we can say that interrupts can be prioritized. So the beauty of this, the microcontroller, is the priority levels of these service routines or the devices can be dynamically also adjusted. That means that through the program, for example, in the first 1 hour of the operation, I can say that the priority of the timer 0 is more. Then after maybe 1 hour of operation, I'm doing some other job. There the timer 0 is not priority for me. I can assign the priority to the ADC chip. Like that, priorities I can assign, or not based on the time at all. When depends upon the requirement of the program, depends upon the logic I have implemented, I can prioritize which interrupt has to be given more priority. So that facility is provided here. So these three concepts are very, very important. What is called as maskable and non-maskable, vectored and non-vectored, and the priority of interrupts. So the LPC2148 provides priority assignment for the interrupts, and which can be changed dynamically at the runtime. Now, there is also called a software interrupt generation, in the sense, for example, you are building a product. Actual devices are not there around the product, but I want to simulate whether the interrupts or interrupt routines are working, the devices are generating proper interrupts and everything. So you can simulate, or you can generate the device interrupt through what is called software. So by writing a proper bits into the register, I can simulate actually interrupt generation, which is equivalent to the hardware. So this is very helpful whenever you want to develop the product. So I can generate a timer 0 interrupt through the software, not by the actual timer module. Even I can, for example, timer 0, whenever it overflows, that whenever it gets a match to the match register, an interrupt is generated. So that action I can initiate by writing a proper bit in the software interrupt register. So that is also possible here. It's useful in the testing of your products. Now let's understand little more details before we start writing the code. Now, having understood the basics of interrupts, now let's go into the details about how do we classify this interrupt. All the interrupts, the 32 interrupt request input. How many interrupt requests? 32 interrupt requests are there. What are those interrupt requests? So I can just show you. These are the different registers. So let's go to, these are the 32 different interrupt requests are available. So, okay. So these are the different requests which generated by the inside the LPC2148 microcontroller. For example, so look at the bit 0 to the bit 31. So the bit 0, that is the first interrupt among the 32, will be generated by the watchdog timer. So if you look at the 4, what we have understood, timer 0 can generate an interrupt. We know that whenever it matches to the match register, it can generate an interrupt. So that is a level 4. That is a fourth source of interrupt in LPC2148. The fifth source of interrupt is timer 1. Sixth source is UART 0, and then UART 1. Like this, these are the different sources which are related to the internal peripherals, and some are related to the outer pins. For example, look at ENT 0. It's an internal, it's an external pin. It's also external pin. So these are the external pins. That means that external devices can connect to these pins and raise the interrupt. So totally, if somebody asks, there are 32 sources, 32 different interrupt sources. Some of them are reserved. They have not given it. It's given in the next version of the microcontrollers, which is compatible with the LPC2148. So these are the 32 different sources where the interrupts can be generated either internally or externally. Now, these 32 interrupt requests, whatever it is generating from the microcontroller, I can group them into 3 types. Group them into 3 types. So what are the 3 types of grouping I can do it? So number 1, I can group. So I can group them as what is called as FIQ interrupt. I can group them as FIQ interrupt. This is a first type of interrupt. So we know that FIQ interrupt is a fast interrupt request, and it is a highest priority. The second one, the second way of grouping is you can make the interrupt as IRQ, and it's a medium priority. It's an highest priority. The third type of interrupt is called as a non-vectored IRQ. It is of a lower priority. What does it mean that? The 32 different interrupt requests which are generated inside the LPC2148 and from the external sources which are coming to the vector interrupt controller can be classified into one of the 3 types. There is no other way is there. You have to classify them as what? Either FIQ or IRQ or non-vectored IRQ. IRQ 2 types are there. One is IRQ vectored is there, other is IRQ non-vectored is there. So broad classification is what? Either you can classify the 32 interrupts as what? Either you can call them as FIQ interrupt, or you can call them as what? IRQ interrupt. Of course, there's a two subcategories in there. Let's focus on the two categories now to start with. Now, how do I select whether I should call, for example, timer 0 interrupt is there. Should I configure the timer 0 interrupt as an FIQ, or should I configure an IRQ? How do you take a decision? It depends upon the latency you require. If you want immediate service, that is a fast service, and you should be higher priority, yes or no, you classify that interrupt as an FIQ. I don't want us to be higher priority, but it should be serviced in an order, correct? Now, then you can classify as an IRQ. So, because if there is a request coming, if there are 32 requests are there, you classify some of them as FIQ, some of them an IRQ. Then what will happen when the interrupt request comes from all the 32 sources? What does a VIC, vector input control, will do? First, it looks up the interrupts which are classified as an FIQ. It services them first, and then only it services the IRQ. That means that whichever the interrupt you make that interrupt as an FIQ will be serviced first because it has got an highest priority. Then the interrupts of type IRQ will be serviced. So when you write a program, this is the first decision you have to take. What's the first decision you have to take? Whichever the interrupt you are using in the program, let's say timer 0, I am using it. Before start the program, I should decide, I want to make the timer 0 interrupt as what, FIQ or IRQ? I should take a decision. So generally, so that much of urgency is not required. Even if it's attended within seconds or something is good enough, I always go for a IRQ. So this is the first assumption we have to make it. Now, after making the assumption whether I require a FIQ or IRQ, correct now. So then I should able to, the second thing I supposed to do is what? I should able to enable the, what is that interrupt, whether it's required or not. So after selecting whether you require FIQ and IRQ, how do you select them? For that, they are provided, a registry is provided. So what is called as vector VIC interrupt select register, vector interrupt controller select register is available. So using the select register, you identify, so which interrupt, which is the interrupt you are taking, FIQ or IRQ. After you selecting that one, so this is a register, vector interrupt select, this is a register. Into this register, 32 bits are there in this register. So 32 bits are there in this register. We can see that register for a moment. So how does the vector interrupt select? We'll come see that this is a register. So this register is classifies each of the 32 interrupt sources as what, FIQ or IRQ. So let's go to the vector interrupt select register. We will see that, how that we have to program that. Yeah, this is a register. So how many bits are there in the register? All these registers, 32 bits are registered. So bit 31 to, so bit 0 is there. The position of all the bits is predefined. For example, always the bit 3 are always bit 4 in any of the registers corresponds to what? Timer 0. So you should always remember that. Oh, timer 0 interrupt is correspond to what? The position among the 32 bit 32 interrupts, the position is 4. What is the position among the 32 interrupts? For timer 1 is always 5th. UART is 0 watt is always a 6th. This is a fixed. You should remember that. So now, so that means that, let's say I'm writing a program for the timer 0. I'm going to write interrupt driven data transfer program or interrupt driven program for the timer. So what should I do it? First of all, I should identify what is a bit number corresponding to that peripheral. Now, since I'm writing the program for the timer 0, the bit number is what? The 4. Then what should I do it? Then one bit is provided for every peripheral. In that one bit, in the bit number 4, what I can write? Either I can write here, 0 I can write here, or I can write what? 1 into this position. So whenever I write 0, that means that what? It is a FIQ interrupt. Whenever I write 1 into that, it becomes what? It becomes a IRQ interrupt. So look at here. What is that? If I write 0, it becomes what? The interrupt request with this bit number is assigned to the IRQ category. The other way. So when you write 0, it becomes what? IRQ interrupt. When I write 1, so the interrupt request with this bit number is assigned to FIQ category. So by default, by reset value is what? 0. That means that as soon as LPC2148 microcontroller boots, all these interrupts, 32 interrupts are classified, categorized into what? IRQ type. So now, so this you have to understand. So this is the first thing I have programmed. So what is the first thing I have programmed is, so I have selected what is the type of my device, either FIQ or IRQ. I have configured that using what is called interrupt select register. Now the next thing we'll go to. Now, as I said, all the interrupts are disabled by default. It is your responsibility to program through the program enable that interrupt corresponding to that peripheral. For that, they provided what is called interrupt enable register. So this register controls which of the 32 interrupt requests and software interrupts are enabled to contribute to the FIQ and the IRQ. So this interrupt enable register again contains the 32 bits are available here. So 32 bits available here. So let's understand that register. So yeah, this is an interrupt enable register. 32 bits are there. As I said, the position for the devices for the bit number is a fixed set. For example, so which is the bit corresponding to the timer 0 in the interrupt enable register? Timer 0 bit 4. This is standard position. Positions will not change. So any of the register, if you want to do certain operations, you'll be knowing the timer 0 means it's a bit 4 in the corresponding register. Now what should I do? Now there are two options you can write it. So all this one, when this register is read, once indicate interrupt requests or software interrupts that are enabled to contribute to FIQ or IRQ. That means that if I require this interrupt, timer 0, I should go in the program, I should write 1 at this point. So by this one, dynamically, you can, at the runtime, you can disable some interrupts, you can enable some interrupts. For example, you're doing very important job. I don't want any interrupts to be enabled. So you can always clear the interrupt enable register. To clear that, there is another register is provided, interrupt enable clear register. You can write the corresponding bits to 1 into that portion, it becomes clear. So by writing into by making this bits 0, I can disable any of the interrupts. So this is the second step in the program we're supposed to do it. So we have understood first is we have to select the interrupt as IRQ and FIQ. Then I should be able to select whether enable the request required interrupts. Now after doing that one, now let's understand a little more details about vectored interrupts. As I said, many of the projects, whatever we are going to do it, we are not going to use FIQ interrupt. We are going to use generally IRQ interrupt because that is good enough for servicing our interrupt request. So whenever I'm going to service my interrupt IRQ type, there are two types of IRQ requests are available. One is called IRQ vectored interrupts. Other is called as IRQ non-vectored interrupts. So I'm going to use in the program whatever I'm going to develop now. So I'm going to use now in the program what I'm going to develop vectored interrupt type I'm using. So what is a vectored interrupt request? Only brief thing we'll understand that. There are 16 of the total 32 interrupts can be grouped into the vector type in the sense, as I said, even though there are 32 requests are available, 32 sources available, and even though I said that every interrupt source can be configured as FIQ or IRQ, but only among the 32, you can only make 16 of them as a vectored IRQ interrupts, not more than that one. That means if you want every 32 bit as IRQ type, only 16 you can make as a vector type, remaining should be what type? Non-vectored IRQ. So 16 are available here. Now, what is the meaning of the 16 vectored interrupts? As I said, 16 vectored interrupt means 16 interrupt service routines you can write separately, and the microcontroller provides a register. In that register, you can map your ISR address and inform to the LPC2148. That means that if interrupt request comes from this slot, you execute this ISR. So what is the meaning of that? Let's go to a little detail about that one. Now, so let's understand this one. So there are, I said, 16 interrupt requests are available, which are called as vectored IRQ. Among the 16, they are named as vectored interrupt 0 to vectored interrupt IRQ vectored interrupt 0 to IRQ vectored interrupt 15. And each of these 16 vectored IRQs, they will be provided what is called slots. They are provided slots. So this is one slot. This is, let's say, IRQ vectored interrupt slot 0. They are provided another slot. It is called as slot 1. So how many slots are there? So there are totally 15 slots, 16 slots are there. They are numbered as IRQ 0 to IRQ 15. These are vectored slots. That means that every slot is a vectored in nature, in the sense. So there are 16 ISR routines. You would have developed it already. You would have kept it for the 16 devices. Now, I should be able to map this ISR program into any one of the slot. In the sense, if I have a 16 devices, which I want to configure them as IRQ vectored interrupts, which device or which ISR should go into which slot is a decision by the programmer. So how many slots I have? I have a 16 slots. So that I can decide, oh, the IRQ 0 vectored slot 0 is mapped to this ISR. I can map. So this ISR I can map to what another slot like this mapping I can do. So which slot you're mapping to which device, it is depend upon the programmer. What is the difference between the 16 slots, all the 16 slots here? There is a difference is there. All the slots are prioritized in the sense slot 0 has got the highest priority. Slot 1 is the next priority. Slot 15 is the next priority. For example, if you connect the device to the slot 0, then that means that this will be serviced first. For example, if you connect, if there are 16 devices are connected to the 16 slots, if the request comes from the 16, it will be attended only after attending what? All the requests from other slots. So based on the priority among the 16 devices, you decide which slot you're going to use for your device. This is what is called as dynamically, you can able to assign, so which ISR to be correspond to which slot. Let's summarize that one now. So as I said, the two interrupts are there for the LPC2148. One is FIQ and IRQ. IRQ, there are two types are there. One is called vectored, other is called as a non-vectored. In case of a vectored, only maximum 16 interrupts can be put as a vectored. The remaining one, you can either use them as an FIQ or you can make as a non-vectored IRQ. These 16 vectored IRQs, each IRQ has got a one slot. So in that slot, there is a facility is there to map an ISR to the slot. Now let's go to the details about the slot. What does each slot contains? Each slot contains two important registers. Every slot contains two important registers. One is called as a vectored address register, VIC, vector address register. How many such registers are there? 0 to 15. So every slot contains one such register. For example, slot 0 contains vector address 0. Slot 15 contains what? Vector address 15. Like that, registers will be there in every slot. And also, every slot contains one more register called as a vectored control register. Vectored control register. So what is this? What is that register? Is that this register, which is provided one per slot, is available to map which device should be mapped to which slot. As I said, there is a freedom is there to the programmer to map the device to the given slot. That means that if timer 0 is there, timer 0 ISR or timer 0 device, I can map to slot 0 or I can map to slot 15 also. It's my decision. How do I map it? That mapping can be done using what is called control register. So every slot contains two registers. One is vector control 0, vector control 1, and vector control to 15. So every slot provides two registers. One is a control register, other is called as an address register. What is the job of a control register? Control register specifies that this slot 0 it should be mapped to which device. Then what is an address register says that? Address register says what is an address of the ISR program for the device which you are servicing it. So this, because of this facility of mapping, they are called as vectored interrupts. So summarizing, every slot has got a two register. One is called as an address register, other is called a control register. Address register will contains the address of the ISR program which you are supposed to execute corresponding to the device. The control register specifies that which is the device among the 32 you are mapping to this slot. So having understood this one, I think we can go ahead and write the program now. So now we will directly jump to the program and understand other some basics later. Now, am I audible? Am I audible?
Yes, sir.
Yes,
Yeah. So please stay back another 15 minutes to 20 minutes. I'll take it because it's an important topic. So let's not continue tomorrow. So now, before I start interrupt-driven program, I want to write a normal program and explain what is an advantage of interrupt, the beauty of the interrupt programs. I've written a small program to generate a square waveform of 50 Hertz. I've used a timer program. So I've loaded 1,50,000 into this one. This 1,50,000 peak clock cycles will constitute what is called as 10 millisecond. So this is, I've written this program to generate 50 Hertz pulse, 50 Hertz pulse I've generated, 50 Hertz waveform I have written this program, 50 Hertz waveform I'm generating it. So how do we calculate this value? We know that. So whenever So 50 hertz means the time period of 50 hertz is what? 1 by 50. So whatever you get, that is a millisecond. Then half time is what? Half of that. Then on time is what? Half of that. Like that I have calculated. So then on time, to get the required on time, this is the value to be loaded. You can refer the timer notes for this. I have calculated for this. I assumed P clock is equal to 15 megahertz. Now, so this timer program, whenever I call delay program, exactly it produces the on time or off time, which is required to generate a 50 hertz waveform. So I'm calling the delay program here. I'm calling the delay program again. So I've used P1.16 as a port number, the pin to generate this waveform. So this is a standard program. You understood this program many times and you have executed these programs also. I'll just run this and just demonstrate. Okay, so now I'll compile this program. So I will see that this waveform can be generated on this one. So I've already loaded in the setup P1.16. So I'll just run this program. So I got a now waveform, I'm getting it. It's a 50 hertz waveform. So to verify that, I'll just stop my screen. So I've enabled signal information. I've checked this cursor. I've checked this one. So I'll set the reference here. I clicked on the mouse. I set the reference. I'll go to the end of the one clock cycle to measure the frequency. I'll keep it here. So you can see that 49.8759 hertz. That is approximately 50 hertz a waveform I'm able to successfully develop using this program. Now, so I'll stop the program. That is, my task is done now. I want to convert this program into interrupt-driven program. What is the disadvantage of this program? Look at here. The microcontroller is polling continuously. That means that microcontroller is not free. Now I want to remove this job. I want to remove this job. I want to make the microcontroller free. That means that. So I will just make the microcontroller free like this. Now what will happen? So here, no code is there. So here, no code is there. Free to do, free to do any other job. To do any other job. So what I'm doing here, I'm just relieved or delegated all the works in the background so that the controller is free now. It can do any other jobs now. See that while one, no code I have left it. But I want to do this job of generating a waveform of 50 hertz waveform in the background. That means it should be happening in the background, but majorly the CPU should be free to do other logics. How do you implement this using an interrupt-driven program? Number one, since I am not explicitly calling the delay program, I don't requirement of this one. I'll remove this one because I'm not explicitly calling. I'm using a timer. I'm using the timer to generate a waveform, but I'm not explicitly calling them. It should happen in the background using an interrupt concept. Let's go step by step and understand that one now. So I will just only copy what is required and then we will do like that. Okay, so now what I'll do is I've written a small code. I'll just paste there. So look at this code for a moment. I want to write an interrupt service routine, first of all. Now, what is my job of this routine is now? So which is the device I'm using? Which is the device or peripheral I'm using to generate an interrupt? Timer 0. So among the 32 devices or 32 peripherals or 32 sources from where the interrupt can be generated, I've selected timer 0. So you know that in case of a timer 0, the slot number is always, the 4th is the slot which was available there, yes or no? So this is a slot number is always the position, the bit position for that peripheral or this interrupt is always the 4. Remember this option now. So what should I do it? Now, I want to generate an interrupt from the timer as soon as the timer 0 overflows. In the sense, the timer 0 counter matches with the match register, an interrupt should come to the main program. So then what I have done here, I should enable the interrupt related to the timer 0. How do we do that one? Number one, first thing, I should be able to write a program. I should be able to write a program and we should be able to enable that one. So the first thing we have to do in the interrupt service routine, select the required, the peripheral, what type of interrupt you want to do it. Is it an IRQ or FIQ? By default, all are IRQ so that I'm not going to write anything into the interrupt select register, not required. Then only thing is all interrupts from any peripheral are all disabled to start with. I have to enable it. So I've written to interrupt enable register. What is that I've written in this register? So which bit position I am supposed to write it? I have to write into bit position 4. In this one, I have to make it 1. So if I make it 1 here, 1 0 0 0, this is a value you're going to get. So what is the value you're going to get? 1 0. So look at that. The fourth D0, D1, D2, D3, D4. This bit I made it 1. So why I made only this bit is equal to 0? I am interested only the interrupt from a one peripheral. That peripheral is timer 0. So I just made it this one. This is the value I got it. Now I have written this value into VIC interrupt enable register. Now that interrupt, that is the timer 0 interrupt, is enabled now. This is the second job I have done it. Now third job, you can make this interrupt request from the timer 0 as IRQ vectored, IRQ non-vectored also. Always in the projects, whatever we do, generally we make always as a IRQ vectored interrupts because it has got a mapping facilities there. So now I want to configure IRQ, that is a timer 0 interrupt, as vector type. As what type? I want to configure this timer 0 interrupt as IRQ vectored interrupt. So whenever I want to configure, two things you should remember that. I can make this timer 0 interrupt into vectored IRQ, but I should know that only there are 16 vectored IRQs are there. In that is 16 slots are there. I can choose any one among the 16 slots and assign that slot to this timer 0. That is what I have to remember it. So which is a slot? You can choose anything. So I've just selected randomly slot number 5. So I am going to allot the IRQ vector slot 5 to the timer 0. How do you map them? How do you allot them? I said every slot has got a 2 register. One is called a control register, other is called as a address register. What does a control register do it? So control register, I have to write a proper values into this one to map timer 0 is corresponding to slot number 5. So let's go to that method now, slot. So I'll go to that register. Okay, this is the vector control register. So which is the slot I'm interested? Slot 5. So I'll write into the control 5. Now what do I write it? So they're provided like that. The bits 0 to 4, that is 5 bits they have provided to map the device to the slot. Why they have provided only 5 bits? Because only there are 32 interrupt requests are there in LPC2148. 2 to the power of 5 is what? 32. That means that in this bits 0 to 4, you should indicate which is the device you're mapping to this slot. Now, we know that the slot number, the device number is what? The 4 for the timer 0. So I'm supposed to write 4 into these positions. So that's what I have done here. So that's what I've done here now. So 24 means what? So I'm the first 4 bits, I'm writing what? The 4 into that. So it is nothing but 0, 1, 0, 0. Etc. So this is nothing but called as 4. So in the first D0 to D3 bits, D0 to D4, 5 bits, I'm writing this number into that one. So that it's completed now. So D0, D1, D2, D3. So D4 is also becomes 0 now. So now, what is the other things I supposed to write into the control register? As I said, so this is called slot enable. So whichever the slot you're writing, that slot you can enable in the sense, there are 15, 16 slots, whatever you have, you can enable them or you can disable them. If disable means it will not work. Whenever you don't require, just disable the slot. Other things you can keep it as it is. So I want to enable them. So which is a bit number 5. So I will write that into 1. So now I'll go to the program. I'll just write into 1 that bit. All the remaining bits become 0, 0, 0, 0. So now if I write this word, it's a no. So what is the value I'm going to get? So this is 2. This digit is becomes what? 2. This becomes 4. That's what I written, 2, 4. Always this bit becomes 1 for any slot you take it. There's no differences there. And this depends upon which peripheral you are implementing for interrupt service routine. So that you have to find out. So by writing 24 now, you are mapping slot 5, that is a slot 5, because you are writing into that register, slot 5 to the timer 0 interrupt. Now finish. Now it's very important that where is your ISR for the timer? So I should write a program, ISR program. How do you write ISR program? It's typically different. 2 underscore. So 2 underscore, you have to give it in the key, and you have to write keyword called as IRQ. So you can write FIQ or IRQ. That means that key identifies, oh, this is whatever the routine is written is called ISR. It's not a normal function in the procedure. So this is where the interrupt service routines comes into picture in the C language or C++, anywhere you can write it. So whenever ISRs are there, always remember that there is some way of identifying that procedure is not a normal procedure, it's an ISR procedure. The written type of any ISR is always the void. Because why? Because you are not explicitly calling and taking the written values. So you are not calling this program and passing on arguments because you are not explicitly calling. It is automatically called at the hardware level. So that is why always arguments is what? Void. Written type is also always void. This is always remember. There is one difference between a procedure and your ISR call. So this written type is void. The argument is also void. And what is the keyword you have to use there? Underscore IRQ. So now this is a valid interrupt service routine. Now writing interrupt service routine is always a different ball game. It's not the way you write the functions. You cannot write it because it's called automatically. You should know what it should do in the program. Now what is my job? Generating a waveform, generating a square waveform. So I've used one variable called x variable. I made the variable is equal to 0. So every time I get an interrupt, that means that every time the timer throws an interrupt. When does the timer throws an interrupt? So whenever the timer counter register matches to the match register, it both are equal, then it throws an interrupt. At that time, it comes to this routine. So what you have to do is the variable which indicates whether the waveform is 1 or 0, on or off. So high or low, that is I'm indicating through a register variable called x. I'm making x is equal to invert of x every time it comes. So first time, if it's 0, next time it becomes what? 1. Next time if the interrupt service routine is called, it becomes 0. You're making what? Alternately 1 0 1 0, so that waveform can be generated. Now what you have to do it? So whatever the based on the value, if it's 1, you set that pin is equal to 1. If it is 0, you set you clear that pin. You make the pin is equal to 0. So this is logic I've written. Like this type of variable, either static variables or a global variables, you have to use. So many times we ask, what is the use of a static variables? Extensively in ISR program, we use a static variable because you have to remember the values when you call for the second time. Either you can make the variables as a global variable or you can use them as static variables and implement this logic. So I've implemented here. Now, whenever after the interrupt is serviced, you have to clear that interrupt because the job is done. So in case of LPC2148, this is the register available VIC vector address register. You have to write always 00. Whenever you write 00, the address of this routine which was loaded at the runtime will become clear. That means that the device is being serviced for the request what is generated. So this is called end of interrupt. So in this LPC2148, this is a method. You have to write into this register 00. Now, so and also every timer or every peripheral has got one register is there where you have to what is called as you have to clear the interrupt flag which is generated. In timers, there's one register called T0IR, timer interrupt register. Please refer the documentation. In timer, there's a one register called interrupt register is there. As soon as the interrupt is generated, it will be flag is set and the interrupt is serviced here. Now, once you finish your interrupt service routine, you have to clear that register. That is, you have to clear the interrupt generated because of the match 0 interrupt. So I have to make that bit is equal to 1. So I'm just writing it to this one. So that means that whenever you write on this one, interrupt is being serviced. Now it's ready for what? Next interrupt from the same peripheral. So these are all what is called as the work we're supposed to do it as soon as your job is finished. The logic is being finished here. I've done this one now. Now I written ISR program. I written what is the logic required here. Now these are some codes I've written to enable the interrupt logic inside the timer and also to initialize the timer to the proper values because there is no delay program. Where should I do it? I should do in the main program. What are things I've done it? So match control register, now I written 3. Generally what we were writing, we generally write the 4 here. Now I'm writing 3 because why? We know that in the match control register, there are 3 flags there. One flag, one bit is for what? The interrupt, one for the reset, one for the stop operation. Now I am instructing the timer on match occurs, you have to generate an interrupt. So that is why I'm making this bit. And also I'm instructing that as soon as the match occurs, please reset the timer counter to 0 and again start counting it. That is why the first 2 bits I'm making it 1 1. So usually we make the D0 D1 D2 bit as 1. Now in this program interrupt D1, I have to make the D0 D1 is equal to 1 1 to generate an interrupt and reset after the match occurs. Now I have done this one. This is again same thing. So 1,50,000 I've loaded so that it should produce 50 Hertz waveform. So now in the beginning, when I do these operations, I just made the timer control register off. Then once I finish all these values, then I'm enabling the timer counter. That's all. This I'm starting the timer counter, as you already know that. So I am disabling here and do all the timer related the logics, that is initializing the registers. Then as soon as everything is over, I'm just enabling it. Now I finished. So what all the things I've done it? I've initialized the timer to generate an interrupt. I've also initialized the VIC vector interrupt controller registers to map the timer 0 to the slot number 5 and configure as an IRQ, and also indicated where is my ISR routine. See that, what is the name of this? Timer 0 ISR. I mapped it here. What is this routine? Timer 0 ISR. So you inform to the vector interrupt controller, that means that the ISR correspond to the timer 0 is what? This routine. So after done everything, look at here. The beauty of this program is this one. No code is executed explicitly by the program. On the background, whenever the interrupt comes, it goes here, does the job and comes back. You're free here. So now let's copy this program and run in the there. So I'll copy this program. So let's compile this program and run that. Okay, so there is no error. I'll just compile this program. So let's pray God. So its waveform will be generated. So I'll run the program. So you got the waveform. See the beauty of this program. So no code is there. You are not calling any code, but my job is done. That is some activities happening on the back side. You can connect this to the LED and make an activity LED in the project. That means that you can do other jobs. On the background, LED is blinking always. So this concept is called an interrupt. How it has been implemented effectively in the LPC2148 microcontroller. Every microcontroller provides an interrupt, but this is very powerful. This the facility what provided here is very powerful in LPC2148. The same method is available in all the ARM controllers. See that even if you stop and also measure, it's a 50 hertz exactly, it's coming. So this is the beauty of how interrupts can be used in the microcontroller to do multiple jobs in the background. So this completes today's session. So if any doubt is there, you can always ask the doubt.